Hello to everyone. Today in last lecture I have tell you about the energy band diagram. Energy band diagram, formation of energy band diagram. What is energy band diagram? Basically the energy band diagram is a collection of electron which forms a band. So that so for that level we can say that it is energy band diagram. I have shown it for a metal, for a bulk, for a material, for some atoms, some electrons. I have shown you for that and that slides also. Okay, today we will as I have told you, today we will go through with some numerical about the basically concept of effective mass. We will go with concept of effective mass. What is effective mass? First of all, what is effective mass? As it seems a newer word, generally you know that F is equals to m into a. So this is acceleration, this is force, and this is mass. Okay, so in general we will do, if if you have remembered that we will do like dm by dt, like that you have they will differentiate it, so it will not change. Okay, so this will not change, so that from there we can calculate something. You have read it about that, but in this case what happened, m is a constant. As you know that in a semiconductor electron moves with a constant speed. Okay, so acceleration is constant for each and every electron. So if it is constant for each and every electron, then how we can say that each and every atom has different position. Even you know that some electrons are reside inside of the shell, like inner shell, and some of are outer shell. So for conduction purpose they will go outside, like for conduction purpose always outer. So you can see here that some electrons are inside inner shell and some are on outer shell. Outer shell electrons are loosely bonded as compared to inner shell. So how we can differentiate that one? So I have differentiate F is equals to F external plus F internal. Okay, so internal forces are different, so for that I am equating m into a. For that reason, if I will go, then it will be m asterisk into a. So I have changed this mass. Now this mass is called as effective mass. Then this m is called as effective mass. If you can realize this thing by a simple example. If you want to move somewhere, and as you are moving, so you have seen that someone is dragging you in forward direction, and two people are dragging you in backward direction. So it is difficult for you to move in forward direction, because it may happen that but still your mass is same, but now due to different forces, more mass will seem to be higher as compared to previous one. So this is called as so now your mass is called as we can call it as effective mass. In last lecture I have shown you about formation of energy band, in which I have shown you L valley, gamma valley, X valley. For that for research purpose, what we have done, from this band we have made a cell. Okay, we have made a cell, and we have assumed in each and every cell, because these electrons are in bonded stage. So if they are bonded stage, so they can move in a closed well, which is potential well is called as. This is called potential well, in which they can move slightly, they can vibrate even. Okay, so these shell they can have, so depending upon the energy they have with respect to their position, like how we can differentiate one electron from another depending upon the position it has. Like 1s2, 2s2, 2p6, 3s2, 3p6. In that way you have done, like 1s2 has lowest energy, 2s2 has more than that, and 2p6 has more than that. Then third layer has more, and similarly like that you have seen. You know that better. So different depending upon the position, the each and every electron has different energy. So how we can differentiate one electron from another? Depending upon the position it has. And from the Pauli's-Wilson rule, you know that no two electrons have the same energy. From the Crowing Penny model, the EK diagram. EK diagram, what is EK diagram? The EK diagram of an electron can be given as like this one. From the Crowing Penny model, actually what happened, like from the Schrodinger, from the Schrodinger wave equation, electron was assumed to be have a behavior like a wave. Okay, after that we have seen, then we have gone through that, so then we can say that the electron has a wave nature. So their energy with respect to position can be shown by this, as referred as Crowing Penny model. What is K? K is basically the position vector on which the atom is located. So it is basically EK diagram. So EK diagram will show you how you can the amount of energy it has. Okay, so if I want to know the energy, then kinetic energy of electron you can know. Basically we will discuss about the kinetic energy, because we will simply bother about the conduction of the electron, that's it. So it can be written as P square upon 2m, which can be written as h bar k divided by 2m. What is this one? H is h upon 2 pi. Modified h bar is modified Planck constant, and this is Planck constant, h upon 2 pi k into upon 2m. So now it is h square k square, and this is E. You can see here I have drawn a curve, so it has a gradient. So how I can resolve it, that one? So by differentiating this one, dE by dk will be equal to h square upon 2m into 2k. Okay, so now what quantity I have got? H square k upon m. So h square k upon m. So now what I can say here, that it is written as P upon m with d by dk into 1 upon h, modified Planck constant. Basically we will go for that. Okay, so 1 upon h. So what is designate? 1 upon h is equal to P by m. So d by dk is inversely proportional to mass. What does it designate? Means if the gradient, if for any curve gradient is steep, so much steep, so the mass of that particular electron is lower. Okay, how I can say? See, this is a EK diagram I have drawn, and this is another EK diagram I have drawn, which has higher d by dk. What is meant d by dk? Means change in value of E with respect to change in value of k. So if I will name these two curves at curve 1 and curve 2, then in which curve has higher d by dk? This is curve 1, you can see here, and this is curve 2. It is more steep. So the value of E is not changing as much, value of K is increasing, while in the case of E this one, you can see its value is changing more rapidly. E value is changing more rapidly as a small change in K. So I can say that first curve electron has lower mass and second curve electron has higher mass. Then first, what I can say, that first curve electron mass is lower than higher. But the mass of first curve electron will be lower than mass of second curve electron. So we can say that from that. Okay, so from now what I can say, now if I will differentiate it again, then d2E by dk square will be 1 upon m into 1 upon h modified h bar square. Okay, this one. So what I can say, so now we can say that as I have told you, this 1 upon h square d2E by dk square is equals to 1 by m. So d2E by dk square is now a constant quantity which is 1 upon m, and it should be positive. And you know, when if the second derivative of a function has positive quantity, then it means then what it has, maxima or minima sort of thing. These things you have read in your intermediate mathematics, so and in engineering also, so you can go through that. Now we have what we have done now in this lecture up to till now. We have gone through the concept of effective mass of electron, which is a new concept. As you better know that mass of electron is a constant quantity, is not going to be changed, but depending upon its position it can be changed also. If mass of electron, it depends upon the position on which it has. If it has inner located, then it means mass of electron is higher as compared to a mass of electron which is in outer shell. So what I have done, I have gone through its kinetic energy, which is E p square upon 2m. Okay, where it has came, p is basically momentum, you know, na? Half mv square. So mv is momentum, from that I have taken, and from for electron purpose, momentum can be written as h bar, h happened to modify Planck constant, into k. So h into k, what is h into k? It is basically momentum. It is genuine only depending upon the position. The electron has its own momentum, so it is genuine one, huh? H square into k square upon 2m. Now I have to differentiate it again. d by dk will be equal to h square into k to with respect to position I am differentiating. Okay, so it is 2k upon 2m. Now 2 will cancel out, and h square k by m will be the upcoming answer. And now what I have done, I have converted h modified h into k as p, and one h is remaining, which I have shifted here. So now this quantity will equal to this one. So from here I can see that d by dk is inversely proportional to 1 by m, mass inversely proportional 1. It means that if gradient of ek diagram is inversely proportional to mass of the electron. So now you can see here that ek diagram is shown here, and there is two curves. I have shown it for simplicity, so that you can recognize there's if it is a first curve diagram, it is a second curve. In first curve, the curve is so steep as compared to second one. So which has higher d by dk? D by dk means like a rate of change of energy with a small increment in k is occur. That curve has higher d by dt. If there is a see, you can see if you move further that k value, depending upon the change in value k, it has a small change, so it has lower d by dk. But in first case it has higher d by dk. If it has first higher d by dk, means it has higher gradient. If gradient is high, means mass of electron is lower. So mass of electron in first curve is lower than mass of electron in second curve. Now what I have to do, then if I will differentiate it again, then I have got a 1 by m. So now it is a positive quantity. I think it will be this amount. I have gone through a silly slight revision, okay, so that you can remember this concept. Now I will go through the Fermi energy. As you have I think forbidden band gap, Fermi level, these things you have already read I think. what about the Fermi energy? Fermi energy is the maximum energy which the electron can attain at particular temperature. As I think you people have read these things. Okay, so what does it mean by Fermi energy? Fermi energy, basically it is the probability, half of the probability of getting an electron is called as Fermi energy. So how we can basically occurrence of electron is purely statistical. Occurrence of an electron in particular position is totally statistical, means it has the probability that that electron is will occur in some position. From Fermi-Dirac delta function, we know that 1 upon 1 plus exponential E minus EF upon kT, where K is Boltzmann constant and T is temperature. I think you people have read in first year electronics, like Vt is equals to kT by Q. This is some quantity have you read. Vt is basically what Vt is volt temperature equivalent. ऐसा कुछ have you read that? What is that one? That is volt temperature equivalent. This is a very important quantity in the designing and what in the further study in solid state devices. What is the value of kT by Q? It is 26 milli electron volt. 26 milli electron volt, and this is a quantity. This quantity is at room temperature, which is at generally 300 Kelvin, This value is constant, that is 26 milli electron volt. Basically, this is the quantity which will convert temperature into voltage. This quantity will convert temperature into voltage. So now what I have done here, that the energy which it has, I have divided this quantity divided by kT. So I am normalizing the energy with respect to kT by Q. Actually, how we will designate the energy of an electron? Energy of an electron can be generally shown in electron volt. Okay, if it is an electron volt and kT by Q is also in electron volt, basically what you are doing here, we are basically normalizing the difference between E minus EF with respect to kT. So kT is the smallest quantity for consideration. It means that, and this is the basic of any electronic devices for any small signal model. What is the small signal model then? A small signal model means for small perturbation for small change. Like I have applied a voltage across a diode, that V now suddenly I have changed across the diode between V plus delta V. So now the change across the diode is delta V. So depending upon the rate of change of diode with delta V, how my diode will going to behave. That will correspond to the small signal model. So what we have done, we have normalized the changes above than this value. Changes below than this value we will not consider. Changes above this value we will consider. That is means we will simply go below up to 26 millivolt or electron volt, not more than that. We will simply go for 26 millivolt up to for that value. Otherwise we will not go for it. Is millivolt, 26 millivolt. Below this quantity we will not go for that. If it is more than that, we will consider. Below this value we will not consider. So for any so you know that for getting the more information about the devices, we will generally do. And one more thing I want to tell you, why we will go for these type of things. Like if you will see your circuit analysis and all the things, you have major use what are type of sources, what type of devices you generally have. Generally L, C, R, voltage source, current source, this sort of thing you have read. L, C, R, you have the different volt ampere equation with that. Okay, V is equal to I into R, 1 upon C integral of I dt, L di by dt. You simply know the volt ampere.